Hello and welcome back. We now start our journey into deep learning and look at the library PyTorch. Modern deep learning essentially builds on one of the two major libraries, PyTorch or TensorFlow. And PyTorch is developed by Facebook or Meta, and TensorFlow is developed by Alphabet and Google. And essentially these are libraries that help us make use of GPUs and have a very efficient way of doing essentially matrix multiplication, plus loads and lots of other convenience functions that help us build neural networks and train neural networks. However, at the heart, they can be used as an optimization library, and this is how we want to start using these to get familiar with a few concepts. So what we want to do is we want to fit a straight line in linear regression, and we can do this with PyTorch, for example, as well. And if we express this statistically, we have the target variable as a straight line plus some random noise. And this is how we generate our fake data. Right? We say we have 100 samples, and then we have a true slope and a true axis, a true point where the line cuts through the axis, and some random noise. And if we make a scatter plot of this data, we can see that essentially really it is a straight line with some noise added to it. You can of course change the parameters a bit and vary the slope and add more noise to it. And now we want to see how we can use PyTorch to fit a straight line to this. One of the first things we need to do is to define whether we can run on a graphics card to speed up the calculation. So we can inquire if a graphics card is available, and essentially we use CUDA. This means that we use the NVIDIA graphics card, which is common for deep learning, and CUDA are the drivers for this set. Otherwise, we'll have to use a CPU, which generally makes it very slow. So internally, PyTorch works with the object called tensor, and there are also other data types. In the sense, they are similar to multidimensional NumPy arrays, and you can convert between them. One of the main differences is that they can be used both on CPU and GPU, and we can define the data type as well. So in order to be able to use PyTorch, we need to convert our data to these tensors. So since we started from NumPy, we can use the convenience function provided by PyTorch to do this. And we need to do the following step. We convert the data from NumPy to PyTorch tensors, specify the data type, and move the data to the device we want to run on. Because if we have a GPU available, we need to make use of it, so we need to shift the data to it. So the following code does this. We can take torch from NumPy, the data type is float, and move it to the device. And then we can print what we have achieved. In this case, we want to fit a linear regression model, so we have two variables to fit, the slope and the intercept of the line. So that also means that we need to define two variables that we can use in our fitting, and we initialize these variables with a standard Gaussian. So that means we draw a random number from the Gaussian distribution, so that when we initialize these variables, they have a well-defined value and are not pathological. So here we already see that we move closer to a programming paradigm where we have variables and we need to initialize them, although we are still in Python. So what we do this, we need to have our slope and intercept and initialize them with random numbers. In other programming languages, we would also have to initialize these variables as well. So once we start moving into this direction, we need to think about more structure in our code. Now that we have defined the variables of our model, we need to fit the model. So in order to be able to do this, so in order to get our straight line, we need to have an optimizer and an error metric. So these are the two ingredients that help us fit the models. And the optimizer essentially changes the value of our parameters that we have defined here in a specific way. And the error metrics allows us to judge whether or not the change that has done by the optimizer was good or bad. In our case, we use stochastic gradient descent as an optimizer. Essentially means that we follow the path of steepest descent and see that if the error matrix decreases, then we keep going in this direction, and if we move away and the error metric increases again, then we move into a different direction. So for now, we use the mean squared error. So this is essentially a parabola. We have the prediction and the true value and average over them squared. So here you can see what the optimizer does. Right? We have a parabola like this, and we want to go to the bottom where the prediction is as close to the true value as it can be. And if we move closer to the bottom of the parabola, that we might imagine here, then we will keep going in this direction. If we start turning up on either side of the parabola, then we will move away from this direction again. We need a small learning rate and do it for 1,000 iterations. So we need to define our optimizer with these parameters. Here, notice we have the two variables. So the optimizer needs to know which variables to work on. We specify the learn rate, and then we loop essentially 1,000 times over the following code. This is called the epochs. We make a prediction. In our case, this is just the straight line. So here are our x values, right? So these are the data, and we have mx plus b. This is our straight line. And to make it a bit more explicit, we calculate the error ourselves. So the difference squared and take the mean of it. And then to be able to plot this later, we need to detach it if we run it on the CPU, on the graphics card, and convert it back into a NumPy so that we have the actual value that we can put into this array up here. Now we make the backward propagation, essentially what we would do in the neural network. Here, essentially, this means we calculate the gradient and then use this information in the optimizer. At the end of this loop, we reinitialize this, put it to 0, so we can start the next iteration. So now we do this 1,000 times, plot the loss function, that is the square difference between the prediction and the true value. And you can see that after about 200 iterations, we have found the correct value. Again, we need to detach all the numbers from the GPU. And finally, we create a plot. So we take a scatter plot of the x and y. This is what we had before, these values. And now we want to draw a straight line. So we create a space of x values and evaluate our function at this one. So here you can see the straight line, right? So we need to have m, remember, was our slope. We need to detach it again and convert it back to NumPy so we can work with it. And the same with the intercept. Detach it from the GPU if you're using it, convert it into NumPy, and then we can draw this as the simple data set. And this is what we have here. And as you can see, within a few iterations, we have obtained a linear regression of these data points.